All right, so let's get going again with Unit 2, if you want to read along on your own. So here, I said that we're not going to talk about loops, but we do have to talk about if-else. So if-else looks harmless enough. It looks just like in Java or C++, but there is a fundamental difference in that in Scala, if-else is an expression. That means it has a value, and it can be used in other expressions. So over here I have an artificial example where I'm putting in if-else, if x greater or equals 0, 2, else 0, and that thing has a value. That value is either 2 or 0, depending on whether the condition is true or false. And then I can use that value inside another expression. And so here I'm just subtracting 1 for it. It's just a toy example. So in other words, if-else in Scala is exactly like question mark colon in Java. And so in fact, you could always use question mark colon in Java or C++. And every right-thinking person will, of course, do that because it is 5 characters less to type. So in Scala, that's the way it is. So there is a bit of an issue of types, and that is that nothing forces us to put the same type in the then and the else branch. Like over here, of course, I put an int each time. But if either by choice or by accident you put in things of different types, then the type of the answer is computed as the lowest common supertype that embraces these two. In this case here, the type is the type any. So there is any is kind of like object in Java, kind of. I'm not going to really be talking about the minor details of the type hierarchy. And so you would see that if I do this here in the worksheet. Then over here the answer is hello, and over here it says any. That doesn't mean that hello has type any. What's the type of hello? It's a string, right? We would hope. Let's find out. Yeah, so it's a string. Okay, so what it means is that z, the variable z, has the type any. Now we never declare the types of variables, and so the inferred type for z is any. So that means now if I were to try to call a method on z that works on strings, like z.length, then that's not going to work. Even though z is the string hello, I cannot call the length method on it. And we'll learn later how to overcome that kind of thing. Right now, if you find that in your own programs, that probably means that you did something wrong. So if you find that the condition, that the type of something with an if-else is weird, it probably means that you did something that you didn't mean to do. Now, the other interesting thing is what happens if we omit the else. Then in this case, the condition was false, and so it's an expression, so it still has to return some kind of value, and that value in Scala is called this thing here, the opening and closing parentheses. So this value here, if I write it down, come on. Oh, it doesn't even get shown. Okay. The opening and closing parentheses is a special value of type unit. Unit is the same thing as void in C++ or Java. And the only difference is that in C++ or in Java, there is no value of type void. Whereas in Scala, there's exactly one such value that's written as opening and closing parentheses. So opening and closing parentheses is a value. I don't know what's the name of that value?
Null? I think it's null, no?
No, it's not null. Null is null. So, right, null is different again. So I believe this value here has a name that must not be mentioned. And so we cannot mention it. And its type is unit. Unit is a type with exactly one value, whose name we must not mention. All right. So you use unit as the equivalent of void. If you wanted to have a function that doesn't return a value, then it would have the return type unit. We'll get back to that. All right. So now on to more about vectors. So vectors in Scala are immutable arrays. To get to the ith value of a vector, you use round parentheses instead of square parentheses. And it takes a bit of getting used to at first because the square parentheses are so familiar to us. But if you think about it, it is more uniform than it is in other languages. So the round parentheses are used both for function calls and for accessing the ith value of a vector, because you can really think of a vector as being just like a function. You give it an index and it gives you the value that's contained there. So how do you make vectors? One way of making a vector is to use the fill method, and you specify how many you want and what you want them to be filled with. Now you'll notice there's two sets of parentheses here, which looks a little strange, and that'll become clearer in unit 3 or 4 of the course. For right now, just type the two parentheses. That's just the way it is. So that gives you a new vector that is filled with n copies of whatever E is. Now, what can you do with the vector when it's immutable? Normally what you do with an array is you change the entries, and then the array afterwards has a different state than it has before. In Scala, instead, you have a method called updated, and you give it an index where you want to change something, and you give it the new element that you want to have put in there. But instead of changing the vector, it gives you a brand new vector with all the other elements unchanged and this one element changed. Now, at first you think, that's going to be horribly inefficient. But actually, it's not quite so inefficient, because a vector, you might think of a vector as a linear expanse in memory, but that's not how the vectors are organized in Java. They're organized in chunks. And when you update one of the elements, then the updated one and the original one share most of the chunks, and only that one of the chunks where the update was happened is separate. So because of the structural sharing, even though you may have 1,000,000 elements in a vector, when you update one of them, you're not going to get a copy of all the 1,000,000 elements. You're going to get a copy of some subset of it, of some sub-range of it. Maybe just a record that says this one thing has changed and otherwise go to the underlying one. So in general, in the last 20 years or so, people have become fiendishly good about designing these immutable data structures. There's immutable hash tables, for example, so that there is a good amount of structural sharing going on when you make an update, and that once in a while they say, oh, the data structure has now become a mess with all of these special rules, and then it quietly consolidates some of them, and all that goes on without you having to worry about it. So don't worry excessively about the cost of organizing these. These things have essentially the same time complexity as the mutable structures that you're used to. So, and you can do this, of course, but it turns out that's not all that common. What's more common is that you make a bulk transformation. So you have a vector, and you you do something to it. So here I have a vector of strings, and I pass a function to it. Now, if you look very carefully, you notice that I was a little bit sloppy here. Oops. I did not specify that S here should be a string. And it turns out that the Scala compiler will infer this. If you have a vector of strings and you give it a function, then it knows that that function must be a function that consumes strings. We'll see more about that in the third lecture. So another interesting thing about fill is that you can make a vector by not just passing in a constant like we did here, but you can also pass a function. So here I would get a vector with 10 random numbers. And finally, there is this interesting thing here. Let's see what this thing does. The iterate method takes two things. It takes a seed value s and an integer. It becomes clear with this example. So here we have bonjour as the seed, and we're going to make 8 entries of it. And each entry is obtained by applying f to the previous entry. And f, in my case here, is the function that drops something. I don't even know what drop does. Let's find out. So if I have a string, then you can see what drop does. It drops the initial character. What does the 1 do? Let's see what happens if I drop 2. So that's the number of characters that are being dropped. Okay, so each time I drop 1 character, so let's see what the whole thing gets me. And so in this case, I'm getting a vector that contains these substrings that get shorter and shorter. So each time 1 element, the function gets applied to the previous one. So now the obvious question, of course, is what happens if I put in 9? So drop is smart enough to, if there's nothing to drop, it quietly does nothing. So unlike the substring function in Java, that would die with an exception. So, all right. So let's have a quick question here. So get out your voting cards. Pick an answer. All right, so who's voted for A? Okay, turn over your cards so we can see what everyone voted for. Okay, so a bunch of C's. What did you guys vote for? What did you vote for?
Abstention.
That's not fair. Vote for something.
I don't really know.
Okay. So the easiest way to find out the answer is to look at, okay, I guess that we should first say, what does Fred to vector do? What do you think it does?
Versus the characters.
Yeah, it makes a vector out of the characters in here, right? Let's double check that. And that's what it does. It makes a vector of characters, and the vector contains the characters F, R, E, and D, which apparently don't get quoted here. All right, so this is a vector of characters. Now we map it with a function. What is the type of this function? So this is a function that goes from car to, well, since there's an and in the middle, it must be going to Boolean. right? So in that case, the output must be a vector of Booleans, because it was a vector of car. We map it to Booleans, and so the only right answer can have been C. Except, of course, if there was some subtle syntax error, which several of you suspected me of, and that's not a bad suspicion, because half the time I make typos when I do these things. And so I always put in D to protect myself. So let's find out if this does, in fact, compile. And it runs fine, right? And it gives me the vector. False, true, true, true. All right. Okay, next, maps. So whenever you talk about data structures, there is, you want some linear collection that's that's the arrays of vectors in our case, and you may want to have sets, and but if you only could have one data structure, if you were stranded on a desert island, and you could only have a single data structure, which data structure would you want? Well, of course you would want to have a hash table, right? You want to have a map. Because anything that you can do with the map, and the map is pretty universal, right? If you have a map, you can make a list by just mapping from integers to objects. If you want to have a set and all you have is a map, well, you just don't care what the values are. You just collect the keys. So a map is like that universal data structure, and in every language that you want to know, you first want to look at how easy or how tedious is it to work with maps. And one reason people love a language such as Python, for example, is that maps are really easy. All right, so the way you make a map is you just say what you want. You put with this little arrow operator here, you say I want Alice to map to 10, Bob to 3, and Cindy to 8. So those are the scores they got on an exam. Then how do you get to one of the ones? You again use not the bracket like you would in Python. You use the parentheses, because in Scala you always use the parentheses for element access. Now, actually, if you think, that is super logical, because a map really is just like a function with a finite number of inputs. What is a map? I say, I want to map Alice to 10. It's a function that the value of Alice is 10, the value of Bob is 3, and so having the same syntax as the syntax for functions, that is actually very elegant. That makes a lot of sense. So with arrays, with vectors, you might say, takes a little getting used to, but for maps, that's why they call it a map in the first place. So what do you do if you don't know whether an element, whether there is a value for a key? In Java, you would have to first check, but Scala has a nice get or else function where you get the alternative. So if Fred is present, then we get Fred's value, and otherwise we get this default value 0 here. When you update a map, you use not the update function, but this plus operator. There must be a function that also does the same thing, but the plus operator is easy to understand. So scores plus, and then we add some more association. And what we get out of this is, of course, a new map, because this is an immutable map. It's a new map with more associations. Again, this is not something that's particularly inefficient, because internally, there is this new thing here, and then there's structural sharing with the existing elements. And it just looks up in this one first before it looks up in that. You can also remove a key by using the minus, and then that removes the value automatically. So each time you get a new map, and we'll see really on in the next lesson how to make use of some of these immutable maps. The third data structure that we need to know is tuples. Those don't exist in Java at all, which is a little unfortunate. They do, I guess, exist in modern versions of C++ in some way, but and certainly they exist in languages like Haskell. So a tuple is a sequence of elements of different types, and a vector is a sequence of values of the same type, but in tuples, the tuples on the other hand have a fixed length, and you can mix the types as you want. So here is my first tuple, and it has values of int, double, and string, and its type is written as, in parentheses, the types of these elements. So let's do this here so you can see this. So you can see here's the type, and here's the value, which is a tuple. Now if I say my second tuple, and I put in my first tuple and false, then you can see the type of my second tuple is, it's a pair where the first element has this complicated type and the second element has that type. And the types can of course be anything you want. So here I have a tuple where the first entry has type int and the second entry has type int to int. So these are all tuple types. If you have a tuple, you want to access its components, and weirdly enough, the tuples are indexed starting at 1, unlike everything else in the universe. So in this case here, if I wanted to do the second element, which would be here, this 3.14, then I have to call the _2 method. That is the name of the method. And so I just use the dot operator, the name of the method. No parentheses, because it's an accessor method. It doesn't mutate the tuple. There's another way of dealing with tuples that's often more convenient in practice. So if someone hands you a tuple, so oftentimes a function will return a tuple because there's more than one piece of information that it wants to give to you, maybe like a value and its location. And then you can use this destructuring convention to access each of the elements. So you say val, and then you put in parentheses the names of the variables into which you want to have the components stored. And if you don't want all of them, you put an underscore. An underscore in Scala there must be like 9 different places where an underscore shows up, but it's anytime it means it's something that you don't really care about. It's like a wild card of some sort. So here we say, I want first to become the initial element, second to be the next one, and the underscore means I don't care about the others. So that's convenient, and generally I prefer to use the second form to take apart a tuple than the dot underscore 1, dot underscore 2. So when I can, I try that, but it doesn't always work. Also, what's interesting is this arrow operator. You've seen this arrow operator on the previous slide. And it's not a special syntax for maps. Instead, arrow is a completely general operator. So let's just look at what is the value of Alice arrow 10. And it's a tuple. It's a pair from string to integer that contains Alice and 10. So all the arrow does is it takes 2 values of arbitrary type and smashes them together to a tuple. And what a map then does is it collects the tuples. So I could, if I wanted to, I could make a map saying by putting in the tuples, and it would work equally well. You wouldn't normally do that because it doesn't look as pretty. And sure enough, in the to-string representation, they put it back to you with the arrows. But that's just a question of beauty. So the arrow operator is just a tuple generating operator. So let's see what I'm doing over here. I have a map of scores. Did I actually put that? Let me put this map back in. And now I'm doing something weird here. I am... Okay, what am I doing here? What's the significance of... So I'm taking each P, that would be each pair, because a map is a collection of key value pairs. And what am I doing with a pair? I somehow turn it inside out, right? Let's just find out. So it flips. It now maps 10 to Alice, and 3 to Bob, and 8 to Cindy. Of course, now inquiring minds want to know what happens if I have two things with the same value. Oh, yeah, should have changed over here. Exactly. Okay, so over here. And then it only took one of them. Yeah. So I'm doing this thing here interactively so that, because that's what people do in Scala. It's you explore these things in an interactive way. And so if you're familiar with something like Haskell, then you're used to the style. But if you mostly work in Java, where you're so used to first making sure everything works before you dare to hit the compile button, it's just a different style of interaction. Oh yeah, so the second one here is, I say, oh, I don't really want to deal with the underscore thing because previously I said, wouldn't it be much nicer to use destructuring? And unfortunately, I can't destructure the parameter values directly. So I can't put inside the parameter here, the x comma y. This is a requested feature, but it interferes with a different feature. So it's not syntactically possible to do everything. And so, so you can't. You have to first capture the parameter, and so then I have to do the destructuring here in a second step, and then I can flip them here nicely. That's just the way it is. All right. So another question here to see whether you can decode the stuff. So I want to know what is the type of result where I make a vector, and I'll show you what this vector is. It's just the vector of these words here. So I'm just making a vector containing Mary had a little lamb. And then I do something mysterious with a bunch of arrows. And I want you to figure out what is the type of this. Okay, you ready to vote? All right, what are your votes? Okay, so I see C's everywhere, so that was too easy. No, I see one D here. The reason it clearly has to, it's not a vector, because the to map here pretty much gives it away, right? So the only possibility would be that there would be a syntax error. Now, of course, we can easily verify that by typing it in. Or did I put in a val? Ooh. You had the right answer. Is that why you thought it was a syntax error? Okay, but it was a syntax error because I forgot the val. All right. Okay, so the right answer in this case is D, because I forgot the val. which is why I always have option D, because I've done this long enough. All right, so last thing I want to talk about in this module is ScalaDoc. So if you've used Java, you're familiar with JavaDoc, that documents all of the thousands of classes in the Java library. In C++, what is there? There's like cplusreference.com or some such thing, right? And that does the same thing. And for Scala, that equivalent thing is called ScalaDoc. And here I have it. And so ScalaDoc looks pretty much like JavaDoc, except it has a few features that makes navigation helpful. So for example, if I want to look up vector, I can type like VEC over here, and then it filters out the matching things. So here I have then the vector. And one of the things that one notices is there is a large number of methods. So generally in Scala, there is the belief that if a method is even remotely worth writing, then someone has written it. And so that's great, of course, because, for example, things like distinct, that doesn't exist in Java as far as I know, but here it does exist in, like here it is. And we have things like drop right, which drops the right in values, seems like a useful thing. There's a drop while that takes a function that consumes whatever the type of the vector is into Boolean, so that's a predicate function that says whether something is true or false. So and it keeps dropping elements from the beginning until that function turns false, and then it gives you the rest. Is that useful? I don't know. Have you ever used drop while? Okay.
I think, yeah, but yeah. Some of these ones we use. Yeah.
So I know that some of them are used, but I don't know if I ever used drop while. But someone out there found drop while and said thank you, and that's what it's there for. There's some other functions that we're going to be seeing that are used a lot, and then there's a bunch of ones that are fairly obscure. But it does mean that as a Scala programmer, every once in a while says, okay, I have 5 minutes between now and lunch, so I'm just going to read up on 10 more of these so that I have them stuck in the back of my brain, and maybe eventually one of them will come in handy. There's some of them that are clearly very obscure, like has definite size. That must come from some very general framework thing that a vector is a subclass of some type, some of which can be finite and some of them can be infinite. A vector itself is, of course, always finite. And you see that up here. Look at this. A vector extends abstract seek with index seek, generic traversable template with. If you ask me what a generic traversable template is, I will never talk to you again. So it's not, what the heck is custom parallelizable, right? So this is something that has to do with the internal construction, that there's a very large number of collections in the Scala library, and of course they wanted to reuse bits and pieces of behavior whenever they put one of these together. And really, ideally, this is something that the programmer would not have to see. And it's something that I've often asked for. It would be really nice if there was a user-level view of ScalaDoc that hid some of these, what really are more implementation concerns. So look at all of the inherited types here, right? So vector inherits all of this different stuff. And so there's no hope to understand any of this. I don't know if there's anyone who really has a firm grasp of this except the implementers of the collection hierarchy. And there's no need to. So the Scala programmer takes the view that this is this wonderful, rich collection, and if we can just make use of it, of the things that make sense to us, then that's great. And no one tries to memorize or to understand all of this.
But maybe you can recommend them how to use the Scala in a positive way.
Right. So first of all, you've seen the filter thing. And so the filter thing is your friend. So if I wanted to know something about the XML is gone. Let's say about map, then I type in map, and then I get a bunch of things that I ignore, like gen map, but there's a map here, and then there's map here, and then, okay, this is concurrent, so that's probably not what I want. And so I would probably want to use the immutable map here, and then that gives me map operations. Now, one of the things that you do also have to understand, we have not yet talked about that, is you see where you see this T here. T means it's a trait that's like an interface. When you click on it, it turns into an O, and that's an object. Static methods, or what we would call static methods in C++ and Java, are called object methods in Scala, and so they are in the O category. When you click on it again, you get either the class or the interface or the trait, as we call it in Scala. So you have to when you want to do something like map dot, where do we have it? Like here we we have just this map thing. It doesn't say new map; it just says map, and that means it's a static method or it's an object method. So it's in the O's. Another thing that you need to know is about operators. So generally, operators are listed here on the top. So let's see with map. Here, for example, we see the plus operator, and that's used to augment a map. And now, unfortunately, this is another one of my complaints here. When you look at this operator here, that is probably a little bit difficult to encode, to decode, because you have all of this guff here that says that plus is parameterized, and there's a super type here, and then you have two elements and a sequence of more elements that you can add to a map like that. We're going to learn more about Scala to decipher these things later. In this case, I would just read the words and then try it out. There's no glory about trying to understand every one of these letters here. Or over here, plus plus, whatever a gen traversable once may mean. Just read the comment and try it out, and it'll almost certainly do exactly what you want. Once in a while, the comments are weird, like this one where it starts with use case. I've never understood why it says use case. Do you ever understand why it says use case? Yeah, what the heck is use case? No, the other part of the comment is pretty clear, but I don't know why it says use case, as opposed to what. So that's just the way it is. There's a couple of things that you have to know, and that is the parentheses operator, which is pretty universal. It appears all the time, is not listed with the other operators. So you don't find the parentheses up here. Instead, the parentheses is called apply. So over here you see apply, and that means to use the parentheses. That's a hard-coded convention that you have to know. And there's a unary underscore minus that does exactly what you think it does. It's a unary minus. So when you see things that look weird, just think it's some kind of collections and move on. There are these implicit conversions that you should ignore for now. So every once in a while you'll see some implicit stuff somewhere. Let's see if I find one. They've started hiding some of them, so that's good. So you may not see any very often, and if you do, ignore it. One thing that's a little bit weird is if you look at, for example, string. Notice first of all that you don't even find string by itself, and the one that you want to look for is called either string ops or string like, and there you find a bunch of methods that work on string. For example, there's combinations. So here it says iterate over combinations. I have no idea what this thing would do, but that's what the REPL is for. Or here, the worksheet. Combinations, I don't know, I'll just say 3. Okay, now I get a non-empty iterator. Okay, so what can I do? Whenever you get a non-empty iterator, the trick is to call toVector. Oh, look at this. It gives me free, furred, fed, and read. So it apparently gives me all combinations of length 3. Okay, let's try this.
With numbers.
What's that?
With numbers.
Oh, it makes perfect sense with. So, yeah, didn't you always want to have all 6-letter combinations of the word amazing? And here it is. Well, that's amazing. So, right, so it's all 6.
No,
Yeah?
M is not in the. Just a minute, because.
So I'm taking the.
Can I look at the result? Because one of
Yeah.
them didn't have the M.
Yeah, because I've taken the 6 letters.
I didn't see, sorry.
Yes, I take the 6-letter combinations
Okay.
out of this string.
Okay. The 6 of.
Okay, so here I'm taking them out of extraordinary. And, how long would that take you in C++? So someone out there, wants this kind of stuff. And so Scala doc looks initially overwhelming, but after a while one does get kind of used to. And so my general reaction is, if I have to do something that sounds like it's general purpose enough, that someone should have implemented it as a general function, then I try to hunt for it in Scala doc. Then I spend a few minutes, try to divine what the name of the function might be, and look at a bunch of likely candidates, and then try out a couple of things in the worksheet to see if one of them matches. And it's amazing how often it does. Also in the case that you need math functions, which we probably won't need for a while, they are hidden in the package scala.math. So when you go to math, there's a package scala.math, and that has a bunch of functions in here, like what you always wanted to have, a tan2. All right, so we have a more demanding lab here. The key here is, of course, don't use any constructs that weren't covered. And so go through this lab now. The other thing that I have is homework. And so the general idea of a lab is you should do it with a buddy. And the lab really, it's just there for good, clean fun. It's for you to gain experience, for me to watch you struggle with something, and for us to look over how far everyone has come. There's not much grading in the lab. It's just what we do to gain more practice. Then there's the homework. The homework is graded, and the homework is intended to be individual work. You can do the homework in class if you're done with the lab, or you can do the homework at home. I don't care where. And the homework is done with this auto-grading system. So let me open up one of these guys here. And so here we have a homework where it asks you to compute primes. So it's a function that generates all the primes between start and some n. And so if you really know what you're doing, you can type the answer right in here. So you can say, well, everyone knows what that is, right? That is start to, obviously start plus n. Is probable prime and certainty. Oh, they can't use filter? Okay, well, the rules are there to be broken. But then I don't know how I intended this to work. And now I've passed all of these 3. Well, that's amazing. So if you know what you're doing, you can type it right in here. What I expect you to do is not to do this, because this is, of course, a terrible IDE. So I would expect you to first figure out this stuff here in the worksheet, and then when it all works. Then you can go, now I have to find some functions, and now I'll say primes. Then you try it out, and I'm not going to do that now to not waste your time. And then when you're all done, then you paste it in. So this is just there to collect the answer. What does happen is after it's done, there is a download button here. So it gives you a zip file, save the file, and then email it. That's the file that's being graded. All right, so that's how to do the homework. If you want to do it after the end of this lab is kind of long, so you might not get done. But as it happens, you have almost 2 weeks to finish it. So it's due at the beginning of next class period. But right now, get going with the lab and have fun and misery with tuples.